All right. Okay, so hi everyone. My name is Yogev Baron. I'm from Tel Aviv University. This is joint work with my advisor, PhD advisor Yishay Mansour, about non-stochastic bandits with evolving observations. So the model here, the motivation here is environments where you don't necessarily receive an accurate feedback on the actions you make. So you can think of maybe you get some information about the action you made, but not all of it. In online ads is like a good example where you notice like the user clicked on an ad, but you don't yet know if he's actually going to buy it, and then later on he buys the product. So like you get more and more information as time goes. Another application that relates to my other line of research in finance is blockchains that can maybe, like in blockchains, sometimes the state is reversed. And then like you think your action made some money, and then in hindsight, after like a minute, you realize, oh, nothing actually happened, or like you actually lost some money. So like in conclusion, the motivation here is that the feedback you receive is not necessarily the same. Is not necessarily immediately visible to you. It may not be accurate, and you don't actually know what the situation here is. So this is closely related to delayed feedback, which is already, there's a lot of literature on the subject. In delayed feedback, you don't get the feedback immediately. You get it after some delay time, these steps. But you do know that like after these steps, you're going to receive it. And when you receive the feedback, you know it is actually the loss you actually suffered. And you know this is the true loss. So like this is some generalization you can think of. So we have some kind of notation here. So the loss, it's kind of confusing, but the loss sub tau and sub t is actually the loss of the action performed at time t as observed at time tau. So like if now you're at time tau, this term is your most updated information about what actually happened at time t. So for delayed feedback, it's going to be like 0 for you don't have any information about the loss, and then after these steps, you suddenly know the actual true loss. And the goal here, of course, is to minimize the regret compared to the true loss and not compared to the feedback. You don't care about the feedback when in your goal. You're only trying to minimize the regret compared to the true loss. All right. So we start by applying this model to the full information case, where you receive feedback losses for every action possible, not just the actions you made. We use a standard X-free algorithm. The standard analysis for delayed feedback under this algorithm is easily generalizable, and we reach a regret that's O of square root of the sum of differences between the true loss and the feedback loss, which kind of makes sense, of course. Like if the feedback loss is very accurate, then your regret is going to be optimal in the order of square root of t. And if they are very inaccurate, then like you don't know anything about actually the actions you made, and it's going to blow up, and like the regret going to be in the order of t. So this makes sense, and it generalizes to like the optimal regret in the delayed setting, which is square root of dt, where d is the delay. So this is the full information case. And then we start analyzing the bandit case, which is kind of, it's more tricky. So there, using algorithms like X-free didn't easily generalize to the evolving feedback model. So we resorted to use FTRL for the regularized leader. So I won't go into details because I'm sure you know, but like you just follow, you choose the probability distribution above the actions that is best. It is the best based on all the information you received so far, plus some kind of regularizer for the probability distribution. What's important to understand here is the model itself in the bandit setting. You continue to receive more information about the action that you made forever, but only for the action that you made. So if I made action 1 at step t, then I'm now going to continue to receive more information about what was the loss at step for action 1 at step t. I'm not going to know everything about action 2 because I haven't made it. I maybe receive information about action 2 in another time step, but only, so I continue to receive forever more information about the actions I made, but only on the actions I made and not anything else. So we use a recent method to analyze FTRL, and our addition to this analysis is the way we treat delay instead of treating it as a discrete feature. Was there delay at this step? Like, did I receive the feedback in this step, or did I not receive the feedback in this step? Instead, we generalize it to some kind of like continuous measure of like how much feedback did I get in this step. So you can see this term lambda, which kind of generalizes the function of the delay. So lambda is the L2 norm of the difference between the feedback loss and the true loss. And so if we use it as kind of a delay, you can see that like the number of delayed steps for some kind of action is going to be like the sum of lambdas. So like if we're like in the worst case, lambda is going to be equal to 1 because like this is the, we assume the losses are bounded between 0 and 1, and then like if it's going to be like for these steps, it's going to be a different lambda is going to be equal to 1 and then 0 forever. Then the number of delayed steps is just the sum over those parameters. And then when we generalize the analysis to use those lambdas, we reach this regret term. Basically, instead of the delayed term of dt, we receive the sum of lambdas, like the sum of number of delays, the same generalization. And yeah, so this is like our main result in the paper. And what's important to think about is that this is not necessarily the optimal solution. We don't have a lower bound. We couldn't figure out a lower bound here. So we don't know if this is optimal. It might not be. I suspect that it isn't optimal. It actually can be improved. But all the existing methods for delayed bandit analysis did not work, did not generalize well to improve this bound. So it kind of hints that some new methods for analyzing delayed bandits are hidden somewhere, and we should find them. So kind of like a hint of why this might not be optimal is that if the delay is epsilon different, if the feedback is epsilon different every time, like it's corrupted, then the regret bound is actually going to be square root of epsilon times t instead of the optimal epsilon times t. So kind of like a hint that this could be improved. And yeah, that's it. So thank you for listening.
Other questions? So just a quick question. So you do not restrict the amount of steps like for which you can receive feedback. Like at some point, this like composite loss, it doesn't end.
Yeah.
Like what would happen if you would? Like would that make the problem significantly easier?
If I would assume that like it's bounded.
Yeah.
Yeah. So I don't think so. So like I have tried to analyze it in the case that, like, I know the delay is bounded by D, but I still, still the best I can do is the same as like in the delayed setting of DT, and if the difference between the feedback and the true loss is very small, then I suspect it still won't be optimal the way we do it. Yeah.
Okay. I mean, I guess the difference would be if maybe you tried to implement it on like toy examples, or you haven't.
Oh, I have tried, yeah.
Because like then you in your with your current setting, like you have t square, like for every time step t, you have to keep up like following up what's going on with the losses.
Yeah.
So you have like computationally speaking, it's heavy, right? If you would restrict the delay, you could actually have finite buffers.
Might be the way we modeled it is not that you need to aggregate all the losses so far. It's like that each time you receive the most like accurate
feedback. I see.
So like you receive the aggregate each time. So you don't like
you don't need to. It's kind of done.
Yeah,
but yeah,
exactly.
if you have okay. But if you implement it, it's kind of you have to do it.
Yeah.
Yeah. Okay. Anyone else? Sure? Okay. Well, then I will close the session.